Fred and Ron are remote, so I will manage the meeting today. We published the agenda sometimes ago, and we have a tight schedule today. So unless somebody has a problem with the agenda, we are going to just start with Warren's talk.
Talk might be overselling it. So hi all, I'm Warren. I've been serving as Ops AD for a long time now. I think that I'm currently in my third term, I think. And while I am still enjoying it, I think it would be useful for there to be a bunch of other candidates as well for the upcoming cycle. So I will probably run again, but I'd also really like some other people to run. So if anybody is potentially interested or just wants to know more about the position or find out what it's actually like, please come and find me at some point. I'm happy to chat, let you know sort of the time investment, what's actually needed, etc. So, look for me. I'll probably be wearing a hat. Come chat. Happy to talk.
Thank you, Warren. So we will start our first presentation. Next. So before next start, I would like to remind every speaker today that, again, we have a tight schedule. We are going to control the time strictly. We hope you can finish your presentation in 10 minutes and save the other 10 minutes for discussion. Thank you.
Get that off the screen.
I already dismissed it, but it's not reflected over there. It's not on my screen, but it's over there.
Well, we'll swing it. We'll do it live. All right. So, long-time listener, first-time caller. For anyone that doesn't know who I am, I'm Nick Braulio. I work for the Energy Sciences Network, and I'm also the...
If I could interrupt you for a second. The volume is very low. Could you come closer to the mic?
All right, then. Okay, so basically, I'm Nick Braulio, the Energy Sciences Network. I'm also the Department of Energy's IPv6 only implementation lead. I'm here to talk about some unintentional behaviors with ULA that we found. So, let me go to the next slide if you can. Nope, that's not my slide deck.
Oh, I'm sorry.
So while we work that out, basically this talk isn't really, and this draft isn't really intended to be we're not trying to solve any problems with it. Essentially what we're trying to do is identify the problem, codify it. And the basics of that are that the behavior of ULA addressing as defined by RFC 6724 is preferred below IPv4 addressing. Now, whether that was intentional or not, sort of not really relevant to what I'm talking about because that is not the way that it is perceived. ULA deployments using de facto best practices for DNS, the way that everyone that I know has been taught, the way that I've been taught is, use the same A record, quad A record for each resource and let the protocol stack decide. Now, when we say let the protocol stack decide, most operational engineers have been taught that IPv6 is the default if it exists. So you deploy a dual stack network, which is by and large what we see the most of in operations. And if you use ULA and you're using proper DNS, or what I have deemed to be proper DNS hygiene, you will never use ULA addressing, which makes it functionally useless for anyone that's using a dual stack network. Next slide, please. So there are obviously some ways to adjust this, although I will assert that operationally they are all very, very heavyweight and not really sustainable. They're problematic to scale across diverse multifunctional organizations. They impose very significant impediments to operations where IPv6 is already really hard to get in the door. In a lot of enterprises, they would require automation platforms that are also, sort of in their fledgling state. And that's not to even mention all of the embedded devices, operational technology, partner guest equipment, and other legacy stuff that, you may or may not see, but everybody probably has some of that. You just have no mechanism for changing what the address table preferences are. So you can do this in Linux. There's been a lot of discussion about this on the list, and I believe Brian Carpenter wrote a Python script that will sort of make some of these adjustments, but scaling that across thousands, hundreds, tens of thousands, whatever devices, even at, even using open source platforms is very difficult to do. So that sort of makes this a little bit more important for IPv6 deployments where it's already difficult to get movement within a lot of enterprise space. Next slide, please. So in addition to that, if you go and look at some of the files in the code, you'll still see remnants of RFC 3484 in actively deployed and up-to-date systems. Now, that was written, 6724, which replaced 3484, was written in 2012. That's 10 years ago. So even after 10 years, we still don't have a full migration over to whatever the current RFC standard is for this addressing. That tells me mean time to replacement, implementation replacement is over 10 years. So that's one of the reasons that we haven't actually proposed a solution to this, because it's going to take a very, very long time to even get it in place. So what we want to do is just codify the problem so that anyone that's looking for it can go find it very easily, because I'll be fully honest, it was very difficult for me to find information on that. I had to actually go digging around in the code, and then I realized that it was kind of there, but not really. And because of that, timeline just doesn't really align with current enterprise deployment needs. Again, where it's very difficult to get things put in place, that changes as major as IPv6 deployment. Next slide. So here's a quick example, very, very simple. This is just something that I threw together in my little lab that I've got. It's just a simple ping that shows you if I've got, the DNS records matching, A record, quad A record, both pointing to the same DNS name, obviously V4 and V6 address families. If I just do a simple ping, which will use the DNS resolution, it will always use the IPv4 address. There are lots and lots and lots of other examples of this. And all of the caveats of applications can decide blah blah blah. Yeah, that's also relevant. However, this is a pretty good example and probably sort of the first order testing that any operational engineer is going to do, and they're going to right away say, well, this doesn't look right. Next slide. All right, so is there any reason not to adopt this draft? That's my question to you. If you haven't read it, it's pretty easy read. It's not very long. It's really straight to the point. It's got a couple of examples in there. And yeah, if there's any reason not to adopt it, let's hash them out. Any questions?
Okay, Ted.
Ted Lemon. So the first question I have is, why is it a problem that when you have the dual stack network, that it doesn't pick IPv6?
Well, so the way that we've been taught, or at least the way I've been taught for the last 20 years, is that you prefer IPv6 if it exists. So if you don't have that, maybe it hasn't been quite that long, but
So what I'm asking
Sure.
specifically is what operational problem does this represent? Not, is it correct?
what operational problem is
Right.
incorrect?
No, what, I'm not asking whether the behavior that you just displayed in the last slide is correct or not.
Mhm.
I'm asking what operational problem it represents. Why is this bad?
Because in an operational network, when you have an expectation of one thing and you see a different one, it causes
Okay,
unnecessary resource expenditure.
So the problem is that you have an expectation that when you have a dual stack network that you're always going to use IPv6, and therefore when you find yourself not using IPv6, that's bad.
I'm not saying it's bad.
Well,
I'm just saying that as someone who has helped support engineers for a very long time, that's not something, it's something that throws them off. And it's something that's relatively unexpected by people that are just coming into IPv6. And so therefore it typically is a bit of an impediment because it's a one-off.
Right. So, I mean, what I'm getting at is that what you described doesn't surprise me at all and doesn't seem like an operational problem to me at all. And so if a lot of people have the reaction that you do, then it's probably worth documenting that if you deploy a dual stack environment, you shouldn't expect that IPv6 will always be chosen. But aside from that, I don't see why there's an issue.
Well, so that's what this draft does. I mean, that's literally the purpose of the draft.
Hi, Jen Linkova. First, let me answer to Ted's comment. Actually, this is bad because dual stack is supposed to be a path to eventually get rid of V4. If you're never using V6, you have no idea if your V6 is working while you kind of assume, oh, I've been running IPv6 for years. So this is actually not a good situation. However, my question is, so I read the draft and I was kind of confused about its purpose because the behavior is actually documented in default address selection RFCs, right? So I'm just curious if the conclusion of the document should be just don't use ULA, use global address space and your problem just go away automatically.
I mean, that's certainly one answer, and I won't say that it's wrong. That would be the answer that I would prefer. Although I did not think that I should be, those of us that wrote this draft, wasn't just me, thought that we shouldn't be that prescriptive with it. We really just wanted to identify the behavior. I would prefer GUA addresses everywhere. However, in the enterprise space, they always go to ULA first. Not always, but in a lot of cases, they will look at ULA first for reasons that I don't think we really need to discuss here.
Like, I understand, but then we probably just say, if you're using ULA, be ready for this, and it basically becomes useless. So there's no reason to have ULAs because they're not going to be used. But if you really want to get V6 experience, use global addresses. And my opinion, it would be much more useful. The document will be much more useful then because it will be actionable. People can read it and come to some conclusions, and we can give them some operational guidance instead of just telling them things which they could probably find in another document if just look hard enough. And actually, I find your slide very optimistic because you're saying that in 10 years, enterprises need IPv6. I'm really glad to hear that because most enterprises do not agree.
I mean, I would say 10 years ago, enterprises needed IPv6, but I don't always get what I want.
Mark Andrews. We got here because ULA having higher preference actually caused operational problems. That's why the current draft, the current RFC says, insert your local prefix. That is an instruction to device vendors to do the work.
Yeah, they didn't do that.
Yeah. We've got an RFC which says do the right thing. If your vendor is not doing the right thing, log a bug report with your vendor. That is the way to fix this.
Yep.
It doesn't take much.
I would beg to differ with that because that's been my life for the last 3 years.
It still doesn't, if you go and say, fix it.
I'm not saying you're wrong. You're totally correct, but that isn't the reality of it in my experience. So I think that having a multifaceted approach is probably a good idea.
And
I think
what-
we should file bug reports for these
Yeah.
things as well. And I do that very regularly.
But at the moment, ULA is talking internally within the network. It's an internal address.
Sure,
So
if it
what
works.
does it really matter for an internal address, whether you're using V6 or V4, to talk to your internal machines?
It's a repeatability thing. If you don't have
There is
consistent
no
behavior,
there is no repeatability when you got two address families.
well, there should be at least an
There-
expectation of it.
Yeah, there is an expectation that if you're talking to a global address, you'll do V6 first.
Sure.
And if you're talking to a ULA, you'll do a ULA first if your vendor has done the right thing. If your
Yeah.
vendor has stuffed it up,
I'm not disagreeing with you. I think you're right, but I've also
And
not
right-
seen that behavior. So I don't know.
that's why it got put in there, so the vendors could do the right thing. Because you need a sync for ULA in general at the border. You need to have the ICMP V6s come back to say your source address was bad.
Yep.
And you have border routers which aren't doing that, which got us to where we are now.
No, I agree with you. I mean, the reason this exists is because the behavior is unexpected. It's not because of anything anyone did other
Well,
than the vendor's not implementing whatever was written.
It's not so much unexpected. It's doing exactly what it was told to do. As far as the device vendor has implemented the optional parts or non-optional parts. There is no expectation that with the current RFC that ULAs will be used first.
Unless
That's your
they're talking
expectation.
to another local address, in which case they should be.
No, because
Well, I mean,
the
you
current
just
draft-
said that.
I would prefer it to be that. I'd use it if the device vendor that you're initiating the connection from has done the right thing, you'll use a ULA. But there's nothing we can really do to fix this.
And again, I'm not trying to propose that we fix anything. All I'm doing is writing a draft that says this is unintended and this is unexpected. So
Well,
that when
it-
other engineers go to test these things, that they can go, oh, okay, well now this is written and now I know what to expect.
Except, yeah. We want them to actually fix the devices and expect.
I completely agree with you on that. That was a bigger apple than I was willing to take a bite of today.
Yeah, so that's why, Jennifer, I agree that the vendors should fix this, but I don't know that they're going to in any timely manner. And then going back to the previous comment, just using GUA would be great, except there's not a lot of address space that if you're not actually grabbing a GUA address space for some purpose to use in things like what you did, Kevin, with building labs and documentation and stuff. So
Yep.
we're kind of falling in between a little space here where things can get.
Yeah, and you're right. So there are some other things as well that are not just the the lab space and other things, which is how I ran into it. There are reasons that organizations don't go get GUA space that aren't just because they don't want to pay for it. There are also small deployments that will enable ULA by default as their IPv6 stack, and those are mostly open source, but they exist out there and are on by default. So, it's not just a case of you should use GUA space, which in general, I enjoy that school of thought. But in reality, there's a contingency that is, measurable that just can't or won't do that.
Okay, Eric Vink, Cisco. I agree with you, it's unexpected maybe, but it's fully intended behavior. But my main point when I'm coming to the mic is to challenge your statement telling that enterprise mainly use ULA. That's not really what I'm seeing. And I'm meeting many enterprise customers, right? Simply this.
No, no,
It's
I'm not
confusing.
saying many of them are using it, but almost universally, I get asked about it. In
Yeah,
one of the
true.
first 5 questions, and you sort of have to lead them the other direction because it isn't really a supportable model in many cases.
Which is true. When I talk to
Right.
end user, they say ULA, oh, like RFC 1918. Then you talk 5-10 minutes, and
Yep.
then UA after.
That's exactly the conversation that I hear over and over again. And that's really what led to this, because, as part of my job, I've been asked a lot of those questions. So I would encourage folks to go look at the list. There's been a fair amount of chatter about this draft. If we need to take the discussion further there, great.
So we have one last commenter from the queue. Cheng Li, you can go ahead.
Can you hear me?
Yes.
Running from Holly. So basically, what I want to say is that I'm really happy to see the draft because we had a lot of discussion on the mailing list, and I'm happy to see the draft, but we may need to have more discuss on the mailing list. Thank you for the orders.
Okay. I guess Cheng said that he wants to see more discussion on the list. So,
All right.
so thank you.
All right. Thank you.
Song Feng. Song Feng, it's your turn. Song Feng, are you on? Maybe we go to the next presentation then. Justin.
Hi, good morning. So this is just an update of the James draft, which is a work between the University of Liège and Cisco. Next slide, please.
lose control a bit. This is so bizarre. Hi, what's going on? Well, I have to open your slide. Hold on. So, go to.
All right. So quickly, the updates from previous version is that we, as expected, we added some vantage points to the cooperative topology. And who says vantage points means new results, so we also included, and we differentiated UDP and TCP as layer 4 because we noticed some differences between the two. And we also made some editorial changes. Next slide. So this is the topology in the cooperative mode. We had 21 VMs spread across the world. We rented them with different cloud providers to avoid the data center to data center trap. And there is no overlay network, so they are going over the public internet. About the methodology, well, no rocket science here, just the traceroute-like technique, although this is with our own library. And what we do is that we test each pair of VMs in both directions. So VM A is the sender and VM B is the receiver, and we do the opposite for each pair. For each experiment, we have a test with UDP as layer 4 and TCP as layer 4, because as I mentioned, initially we were suspecting that we might have some differences between the two. And spoiler alert, this is the case. So, but the experiments, we tested by open destination options, and we varied the size, because again, we suspected that the size could matter. We also tested each routing type header from 0 to 6 included. We tested fragment headers, so atomic and non-atomic, and we also varied the size. So basically, we just set the M flag to 1 or 0. About IPsec, we tested authentication header and ESP. We also tested with no next header and also with Ethernet as the next header, so based on RFC 8986. And for each experiment, we try without extension header as a comparison, so we'll see the result right after this. And what we do for the probe traffic is that we marked it with an email address, so that entities could identify us, and it is based on the draft that you see on the screen. So the tricky part here is that if you want to be able to attribute the drop to a specific autonomous system, well, you will face a lot of routers that do not respond. And so for the first figure on the top, you see that the first 2 routers responded, and then nothing. And actually, this is what we saw very often. So if this is the trace without extension header, and then you made a test with an extension header, if there is a drop somewhere on the path, it becomes hard to guess which AS is responsible for the drop. So this is something that we have to improve in the algorithm. And next slide, please. All right, so the interesting part. So for the hop by hop first, this is in red, obviously, because this is very bad. So if you take the first row with the length of 8 bytes, you see that you have roughly 9 or 10 persons going through. And obviously, if you increase the size, so if you take 256, you roughly have 3 persons. So this is very bad, and it goes worse if you increase the size. So overall, you cannot rely on hop by hops if you want to use them over the public internet. About the destination header, it's in orange this time because you have some good and some bad. So if you look at the UDP column from size 8 bytes to 24 included, this is reliable. And once you reach 32, you see a little bit of drops. So this is still good, but you cannot call it reliable anymore. But the big drop that we noticed is once you reach 64 bytes. And it goes worse and worse when you increase it again. Again, here you see some differences between UDP and TCP. At that time, we have no explanation, but we will investigate it for sure. Routing headers in orange too, because some are good and some are bad. The ones that are going through are types 2, 3, and 5 and 6. And actually the ones that are not reliable, not that bad, but still unreliable are types 0, 1, and 4. And this is not really a big surprise here because 0 and 1 are supposed to be deprecated. And type 4 is segment routing. So this is actually quite a good news from a security point of view. Back to red, so for the fragment headers. Well, the non-atomic is not that bad, but again, you cannot call it reliable. And obviously the atomic with the M flag set to 0, you have 1 chance over 2 to go through. And oh, green, good news. So not to be so excited about the first one because this is the no next header. So you obviously have no extension header here and no layer 4 header. You have Ethernet as the next header, which is going through. And good news for IPsec, AH, and ESP are all going through. So what we can learn from this is that hop by hop, again, you cannot use them and think they are going through. Destination options, you have hope until a specific sizes. And we have, I think Nalini is there, she has a draft about a destination option, not only for limited domains, but for the public internet. So if I'm not wrong, I think her option is maximum 40 bytes long. So I think there is hope for this option. And this is actually a use case for the public internet with hop by hop or destination option, which is a good thing. So what we plan for this draft is to continue measurements with the wild version. So up to now, we had a specific testbed with 21 VMs. Now we want to probe in the wild on random prefixes. And actually, we already have some, let's call them earlier results. And the trend, this is still to be confirmed. And the trend is that it's like the same that we observed. Some are improving, some are not, but basically this is the same. We still have to test a lot more because the more you test, the more complete you are and the more representative you are from the reality of the entire internet. And as I mentioned earlier, we are trying also to improve the AS drop attribution algorithm. So this is a work in progress. Initially, it was a student responsible for this work for his master thesis. but we have taken it now. So it's in progress, in good progress. So you can find everything you want about James. We have gathered everything on this repo. If you have any questions, thank you.
Yeah, Nalini Elkins, Inside Products. Yeah, no, this is very, very interesting. I think we've talked a bunch about this, and it would be very interesting to find out exactly why. And we're already collaborating because one of the things that we have seen is that there are certain routers which have bugs, which keep hop by hop going out at the source. And so anyway, so what we're doing is we're expanding our testing because we have done some testing to see, because we've had, our results are to the contrary. We've shown large FTPs succeeding, but we need to test more because, it's only from, 2 or 3 continents that we've done it. And so I think we all need to find out more about exactly where and why things are being dropped. Is it at the destination network? Is it bugs or defaults? Quite what? Yeah.
Yeah, sure. Because actually you can do a lot of tests and they might succeed. And so that's why you need to test as much as possible.
Is Fernando in the line in front of me? No? Okay. John Linkova. First, sorry.
Oh, please, go ahead.
No, you were first. Go.
Okay. Can you go back a couple of slides in the measurements slide? Because I have a couple of questions in there.
Which one?
The one with the results. Yeah. So I have a one question and one comment. The question is for the results for the routing headers. I would assume that you used what size did you use for the routing headers for the measurements? Because for the other ones like destination options, you'd use different sizes, and I would expect that you'd get the same thing for routing headers too.
Well, you mean how many segments we had it?
Yeah, essentially, what's the resulting length of the extension header chain?
So basically, this is only one segment, and we also tested with a basic one with 0 segments, but we can for sure try to expand it to see if there is a difference.
Because my expectation would be that the results are going to be like similar for destination options, not necessarily the same values, but as you increase the size, and certainly when you hit like 64, you're going to see like big drops as for destination options.
Yeah.
And my comment is, you were wondering about the differences between, the result for destination options for using UDP and TCP. The length that you have in the table is for the size of the destination options header itself, right?
Yeah. Only the extension headers for each types.
Yeah, so my take in there is that obviously the UDP header size is smaller than the TCP one. So at the end of the day, for the same length of the extension header, the resulting length of the extension header chain is going to be longer for TCP. So at the end of the day, what matters is the result of the the whole length of the IPv6 extension, the IPv6 header chain. So for the same value of the length of the extension header, for TCP, it results in a longer extension header chain. That's why you get like higher drop rates.
Yeah, that would be an explanation because you can see a shift of 1 row between UDP and TCP. Thank you.
John Linkova. Yeah, to follow up on Fernando's comment, for TCP, you were sending SYN packets, right?
At the moment, yeah.
So I guess, yes, the reason might be the router might need to see SYN flags. And if your TCP flags go in behind the value router can like routers copy on chip or something, like looking for the flags, they might just not see the packet as being TCP seen and as a result drop it. So what I'd like to say is that ESP is actually a very good example proving that extension header works when we need them.
Sure.
Like when mobile phone makes a Wi-Fi calling, it's using ESP, right? So ESP has a very good use in internet and it works.
Yeah.
So all like in most cases we've seen packet drops because there is no reason for that packet to go through anyway, right? So I think again, when we saying that we cannot use extension headers on the internet, we need to find good use of them, which would benefit users in general, and then I guess the situation will change. Yes, obviously the random packets are dropped.
Totally agree.
Heard? We have the Mr. Heard from the queue. I think that he dropped from the queue, so we'll switch to next speaker.
Thank you.
Let me see if I can get this share screen to work. Something you are on again. Something, can you hear us? Well, maybe I will do my presentation first. So because I need to run the slide, please allow me to talk from here. Actually, the screen is showing. Fred, if you are online, can you stop the polling, because my screen is the polling and it's here, so it's a bit very confusing. But anyhow, this is our second version of the draft. We basically proposed some guideline for enterprise to deploy IPv6 first hop. Well, it's not working, so bear with me. I have to change to.
Keep hanging, your audio is being lost.
Yeah, it's because I need to switch to share screen. Otherwise, I cannot control the slides. It's very strange. I'm still seeing the polling on my screen. Yeah, you folks are fine, but look at here. My screen is still stuck with this polling.
I wonder why the screen turned up. Anyway, let me see if maybe it looks better from my machine.
Okay.
So, you want to share slides?
Yes, go ahead and put this.
Slots are already taken. So, nobody says that they're sharing. That's weird. Okay, which slides? What is it?
This one. This one. Yes. Okay, it works for you. So we made this draft to provide some guideline for enterprise. And the reason we need that, can you go to the next page, is because over the time, more than 30 RFC has been proposed on the for optimization solution for ND. It's not easy for people to get all of these because there are so many RFCs. And therefore, let me see here. Something started to fall. Yeah, so I am a little bit distracted. So I think that, with so many RFCs, there are two issues. First issue is that, some people may not know, and they deploy the ND and the first hop, and later they find out. And therefore, when later, after you have already deployed, you find a problem and you need to fix it, then it's more difficult to change. The other issue is that you may know, and it may scare you that, oh, there are so many issues, therefore, I would like to stop. And this is why we believe that having a complete draft summarizing all the issues is good, because just like RFC 1999, in the past, I met multiple operators and they are concerned that, oh, IPv6 have a lot of security issues. But once we say that, oh, we'll have RFC 1999, and it summarizes all the IPv6 issues, we also provide solutions. People feel much more comfortable. And so this is what we are trying to basically do the same thing. Next slide, please. So in this draft, we basically summarize all the ND issues known up to this point. And in this version, compared to the previous version, a major improvement is that we now clearly separate the cause of the issue and the consequence. Because in the previous version, we kind of like, we talk about multicast issue, we talk about performance issue, but many of the performance issues are actually caused by multicast. So in this version, we clearly separate out the cause and the consequence. And there's only three causes. The first cause is multicast, which can cause performance and reliability issue. The second issue is that ND trusts all the hosts. So if certain hosts in a public access environment cannot be trusted, then you will have a problem. This is some other issue. And that's the third cause is that NCE is installed on demand. And this can also cause some issue. So in this version, we make it much simpler to identify the cause. And also, if you can eliminate these three causes, then many of your ND issues will be eliminated. Next page, please. Can we go to the previous one? I think that. Yes. Okay. Next page, please. So after we summarize the cost, we review all the optimization solution already published. So first we talk about each what does each solution do, and then we also point out which issues these solutions solve in the table. So for some enterprise people, if you have a concern with a particular issue and you want to find out which solutions is capable of solving these, then you can go for this table and you will know it. Next page. So overall, we also learn a lesson from all these solutions. The solution didn't clearly talk about isolation, but when we look at it, many of these solutions actually have a common thing, which is to isolate hosts to solve the issues. And this is a good lesson. And also from all these solutions, we find out that there are four isolation methods appear in different drafts, but we extract them out. Basically, these are the, link isolation is separating hosts in layer 2. And then there's also the subnet isolation, which is to isolate hosts, giving each host a different subnet prefix. And then there's the GUA, we call it the GUA isolation. It's basically the original ND approach, the ND approach, which is to set the prefix PIO, the L bit, to 0. In this case, the host will not host communication with the GUA will go through the router and will not communicate, the host will not communicate directly. But the LLA, they can still communicate directly. This is why we call it the GUA isolation. And then there's also the proxy isolation, which means that, you have a proxy represent a group of hosts. And for other hosts, they will only see the proxy, they will not see the individual hosts behind the proxy. So this is also a point of isolation. And with this 4 isolation method, if they are independent, then there will be 16 combinations. But we point out that they are not independent. So long story short, in the end, there are only 4 meaningful combinations. There are only 4 meaningful. And the first one is the strongest, and the last one is the least less strong. So all of these will. Can we go to the next page? We discussed that you can use these 4 combinations to isolate hosts. So in the draft, first we discuss, for each combination, what are its applicability? Meaning that what is good for, what is what's the disadvantage? With the applicability, we then explain for each application, for each combination, what is the applicable scenarios, what are the entry requirements if you want to use this combination, what are the requirements you must have, and then after you use this combination, what kind of issues are still remaining, and what you may need to do. So basically for each of the combination, we explain all of these. So these kind of like provide a systematic way for an enterprise. For enterprise, the scenario can be, there are many scenarios. And therefore, by providing a systematic guidelines, enterprise can kind of like go through the list so that they can decide, okay, for my first hop, what will be the best solution? So this is the idea of the draft. We now believe that the draft is in a very good shape, and we hope that people will read it and provide comments. And at some point, we probably want to ask the WG for adoption. Thank you.
Jen?
Jen Linkova. Obviously, if you can isolate hosts on broadcast domain in /64, right, all your problems solved, great. But we all know it's not always possible because hosts might want to talk to each other. So my question is about what you called GUA isolation. It kind of means you trust in the host, right? But the whole idea is you're not supposed to. What prevents a host to ignore LBIT and just send a neighbor discovery packet to its neighbor? So if you are not providing actually layer 2 isolation, and you obviously are not providing it because you cannot. So I'm trying to understand what's your threat model and what kind of issues you are preventing by setting LBIT to 0. Are you assuming all hosts to do the right thing?
Please don't just look at this, for example, GUA isolation, kind of like by itself. We are basically going through a list, starting from the strongest isolation. Therefore, if you feel that, oh, these hosts cannot be trusted at all, then you probably want the stronger, isolation method. You will not even get to the GUA isolation.
Yeah, but quite often you cannot do this because hosts might need to talk to each other, especially all this, like special systems. I'm not talking about laptops. I'm talking about like building management systems and so on. They must talk to each other. So I'm basically trying to understand what kind of security and threat preventions you are getting by item number 3. Because my understanding, you are assuming good behavior of the host in this case.
No, again, when we get to, if you get to GUA isolation, we will point out that, the judge point out that, it solves certain problem, but there are other problems that it does not solve. Therefore, if you are with the GUA isolation, if you are concerned that the host cannot be trusted, then you may need to, add the filtering, etc., to deal with that. So it's not that, you get to a GUA isolation and GUA isolation will take care of everything. It's not what our judge said.
Okay, thank you. And the second question, if I may, you mentioned you might need to have a proxy, neighbor discovery proxy, right?
Mhm.
As far as I know, the existing RFC is kind of experimental. Do you rely on the behavior described there, or you assume some other kind of behavior from proxy indeed?
We don't really assume anything. We simply point out that, in the market, there's such, proposal. So we want to kind of like bring the awareness to the readers and potential deployers that, there are such a solution that you can consider.
Yeah, well, sorry, what I'm trying to say is proxy ND might not actually exist in most implementations, or at least we do not have like standard RFC for that.
Okay, I'll look into that. Any more people in the queue?
Not seem to be.
Okay, then we go back to.
Excellent, and thank you very much.
So next, who do we have? Next one.
So Xipeng, I think Chongfeng is online now.
Now, can you hear me? Okay, sorry for some small problem. Hello, everyone. Thank you for giving me this opportunity to present a framework on multi-domain IPv6 only analysis. Next slide, please. Next slide. Okay, this is an overview of the drafts. In IETF 113, we presented the requirements to multi-domain IPv6 only network. Based on the comments received, the new draft focuses on framework, and the title has been changed twice. So this case is one draft, multiple titles. Okay, next slide, please. Comments have been received from V6OPS. All are appreciated. Next slide, please. Since IETF 113, the following revisions have been made. The document architecture is adjusted to make the logic straightforward, and the section of scenarios has been merged into other sections based on the comments of Xipeng. And some requirement items have been deleted. We add an illustration how the new framework deals V4, V6 conversion compared to other solutions. We also made some editorial changes. Next slide, please. Yeah, this topic is about operation of large-scale networks. Multi-domain means network is composed multiple AS, and as mentioned last time, different AS may serve different scenarios, such as metro network, backbone network, 4G or 5G, mobile calls, cloud data center network, etc. Also, there's so many IPv6-only techniques, but challenges or issues are still met when planning IPv6-only in networks. I'll give some brief introduction. The first one is partial IPv6-only deployment. Some domains are IPv6-only and others are not. The second one is unnecessary traffic winding when stateful V4V6 gateway deployed at the edge of a backbone. The next one is invisibility of the original addresses. This means that when SRVCB is used to encapsulation IPv4 packet in IPv6-only network, the out IPv6 head contains no original IPv4 address information. The next one is inconsistent data format. Some domains use translation, some domains encapsulation, this lead to excessive conversion gateways and the network complexity. Next slide, please. So there is a need for multi-domain IPv6-only solutions to eliminate unnecessary conversion functions, improve data forwarding efficiency. The following requirements should be met by the new framework. They have been introduced last time, so I think this part can be skipped over. Next slide, please. For IPv4 service delivery over IPv6-only network, IPv4 packet will be transformed into IPv6 by translation encapsulation in UE or at the edge of the devices. Then the forwarding IPv4 data in the form IPv6 packet will follow the topology of IPv6 network. This is easy to understand, right? But in the new framework, each PE edge device will be identified by at least one IPv6 mapping prefix. It will also have one or more associated IPv4 prefix, which are extracted from local IPv4 routing tables or address pools. The mapping relation between IPv4 address block and IPv6 mapping prefix is called mapping rule in this framework. The mapping rule will have at least the following data structure, IPv4 address block and IPv6 mapping prefix, and maybe include other information in the future. So these mapping rules can be transmitted across domains. It gives the direction and the egress of IPv4 data transmission in multi-domain IPv6-only networks. Using mapping rule exchange, the egress PE can tell other PE that if the destination address of IPv4 packet is within the scope of IPv4 address block of the mapping rule, please send them to me. So the ingress PE can use the mapping rule to generate the corresponding IPv6 address by appending IPv4 address to the IPv6 mapping prefix. This works both for source and destination address. This kind of packet is called IPv4 embedded IPv6 packet. So we can see that rule-based mapping is prefix level mapping. There is no need to maintain user-related states or translation tables at the PE devices. Next slide, please. Next slide, please. So this illustrates the framework from the perspective of adapter in PE devices. Adapter is a functional entity in the PE device which implements a conversion of IPv4 packets into IPv6 for IPv4 service delivery. It has three components, which is the first one is rule management layer, deal with the management of mapping rules. The mapping rule database in the PE store all the mapping rule records it receives. The interface with the adapter of other PE is used for the exchanging of mapping rule with each other. The interface with routing processing layer is used for the transmission of mapping rules. So the underlying routing processing layer is in charge of the exchanging of mapping rule with other PEs and its related routing information. So to support the transmission of mapping rule at the routing layer, maybe in the future BGP4 plus protocol or other control protocol will need to be extended. Data forwarding layer provides forwarding function to a native IPv6 packet and IPv4 embedded IPv6 packet. This framework supports both translation and encapsulation for IPv4 data delivery. Next slide, please. Here, I want to further illustrate the gap and how the new framework address the gap. You know, in IFC 5565, the software mesh architecture, the software tunnel requires address a remote software endpoint to be the same as the address of the BGP next hop, right? The BGP next hop is used for the tunnel endpoint. This is okay for single domain network, but in multi-domain networks, for the given IPv4 address block, the BGP next hop value of different domains are different, but the ingress PE can only see the next hop address of ASBR in the same domain. And it is difficult to obtain the next hop address of other domain to set up end-to-end cross-domain tunnels. Therefore, the procedure in IFC 5565 does not work well in a transit core consists of multiple domains. This has been mentioned in IFC 5565. So here we should use a new framework to how to address this issue. This is sample flow of IPv4 service delivery over IPv6 only underlay. Firstly, the route corresponding to the mapping prefix of the egress will be announced through the whole network. So the ingress will know how to forward the IPv6 packet to the egress. Secondly, the mapping route will also be exchanged between the ingress and the egress PEs. This step should proceed to the process IPv4 data transmission. Otherwise, the data already from IPv4 packet will be dropped due to the absence of the IPv6 mapping prefix corresponding to the destination IPv4 address. Thirdly, when an ingress PE receives IPv4 packet from a client-facing interface, it looks up its mapping rule database to find the mapping rules which best match the packet destination IPv4 address. Then the ingress PE must convert IPv4 destination address into IPv6 destination address using the mapping prefix and forward it to the egress PE. With this new framework, IPv4 embedded IPv6 packet can traverse multi-domain networks. Next slide, please. We have conducted a field trial between two cities in China. One is Wuxi Metro Network, Metro Area Network, and another one is Huahao Cloud Data Centers. The distance between the two cities is 1,700 kilometers. The field trial covers three domains: metro area network of Wuxi, IP backbone network is AS number is 4134, and the cloud data center networks in Huahao, which are different domains. The field trial has no functional requirements to the IP backbone. The backbone only needs to know the passing of the routing corresponding to the mapping prefix. So we deploy the PE devices, which is adapt capable in the production networks. Different PE are configured with different IPv6 mapping prefix. They jointly create a multi-domain IPv6 only network. Mapping rules are pre-exchanged between PE devices. The network can support native IPv6 packet and IPv4 embedded packets. It also can support the communication initiated from the outside. So it's open. Based on the implementation and the trial, next slide, please. Based on the implementation and the trial, we found that this framework works well. It is scalable and can integrate with existing IPv6 only approaches such as 464 Accelerate. In addition, this IPv6 only model can naturally be extended to multi-domain networks operated by different operators, right? So next, further refinement document will be made to consolidate the requirements and further stabilize the text that describes the framework. We're also looking forward to receiving more comments and contributions as usual, and we hope that it can be adopted as a working group item. Thank you. Any question?
Jelinkova, I read the document, and to be honest, I'm slightly confused about the requirements because, for example, the first requirement says it should be beneficial for wider IPv6 adoption. I'm a bit confused how to find out if particular solution satisfies that requirement or not. Secondly,
okay.
Yeah.
Go ahead, please.
Secondly, yeah, I am not sure why you even mentioning SR V6 as a requirement, because I not sure that we shall be mandating any particular technology, right? People might want to use some other technology, so I don't think it's like should be in the document. And third, like the document says, no additional security compromises. From risk assessment perspective, it might be not true, right? You might agree to accept some risk if your risk assessment shows that benefits of the solution exceeds potential impact. So I do not think it's fair to declare that solutions should not add any potential security issues. Thank you.
Okay, thank you, Jane. For your first question, actually, for our network, this is about only. So our purpose is to close IPv4 functionalities at the Annealing network. So, so the packet forwarding and routing will be IPv6 based, right? Of course, we cannot suppose that all the service is IPv6 based, because this is not under control of operators. So we hope that the network analysis should be IPv6 based. So I think this will be helpful for IPv6 development. As actually, which has been done by some operators, for example, 4x, 4x late, which has been done some operators, which is close the IPv4 at the network layer and IPv4 services, right? So this is the first question. And the second question about SRv6, yeah, I think this is a further discussion, but from the standpoint of our operator, for example, China Telecom, we think that SRv6 is a very valuable and useful. It simplifies the protocol architecture and it has been widely used in many scenarios. Yes, maybe different operators have different understanding, but we think this should be considered in this framework. Then the next one is about the security, right? Yeah. In this mapping rule-based framework, the key device mainly implements the mapping rule management and the conversion between IPv4 and IPv6 packets. Actually, it's some kind of router, right? And the converter is static. There's no state maintained at the edge of the network, so it does not introduce too much security issues to the whole network. Of course, maybe the mapping rule exchange will be based on BGP-like protocol in the future, but this is there's maybe some issues which is based on BGP4 protocol. I think this can be discussed in other future documents. That's my answer. Thank you.
Okay, Ron Bonica, Juniper Networks. I have two questions. I'm also confused by the requirements section. The first question is, for what networks are these requirements? All IPv6 networks? A few like China Mobile that you've just mentioned? Or maybe a class of them like provider networks? The second question is about SRv6. I would like you to add text that explains why it is a requirement for SRv6 to be available for networks that require neither traffic engineering nor VPN services.
Thank you, Ron. Actually, the first question is about what kind of network is talked about in this framework, right?
Mm-hmm.
Yeah, this as the title shows that this mainly talks about Annealing network, which of course should be IP based. It should be IPv6 based Annealing network. Maybe on the overlay layer, some such as VPN and SD-WAN, maybe some overlay service which we can support dual stack, but from the Annealing network, we think that it should be IPv6 only based. Yeah. The second one is about SRv6. As I has mentioned, that different people may have different understanding to these issues, because SRVC is a new thing, right? It is still in a stage of trial, and maybe some is stage deployment, maybe some trial, but I think this can be deserve further discussion in the future. I don't think this is a very SRV6 is not closely related to the framework right now. We can have further discussion in the future. Do you think this is okay?
Certainly. There are other traffic engineering mechanisms, SRM, PLS. Many networks don't require a traffic engineering mechanism at all. So why should they? Why should they be doing this? But in any event, let's bring this to the list. Oh, by the way, no hats on for this comment.
Okay, yes, I think, yes, this is a big topic about SRV6 and some peers, and actually it's a separate topic. We can discuss this offline if you think it is necessary.
Folks, we need to move on. So please take the issue to the list. So now, Marie, you are on. Marie, can you hear us? Marie, can you hear us? So it's that. Then we move on to the next presentation. Marie is now back. Can go after, I guess. Marie, can you start? You are muted.
Can you hear me now?
Yes.
Okay, perfect. I can barely hear you. So, okay, so thanks for the opportunity, and sorry I couldn't be with you all there in person enjoying that humid weather. So V6 domain transition, I had the opportunity to lead the transition for Cisco.com. Next slide.
You are too loud, so maybe a little bit away.
Oh, sorry. It's okay, thank you. Okay, so, hi, is this better? Is it better?
I think so. Also, I think Eric's going to go
Okay.
turn down the volume. So it should be nice.
Okay, thank you. So this is just an idea of the scale of the.
我后来换了电脑，又换浏览器，换了 Chrome， 那个它就对了。换成苹果那个电脑。
So we had 33 top level teams. We had 800 plus applications, and by applications I mean external facing web apps. These were not count. This does not include the internal applications. And then the number that really stands out is the 69 authorizations we had to get. The project was so large that we had to get 69 directors or senior managers to sign off on the project. And if they didn't, then none of us would have been able to move forward. And I'll tell you why that was in a little bit. The big win is that we enabled 40 billion of Cisco's annual run rate. Next slide. Excuse me. So the domain transition was very public. It's obviously tracked. It's very visible externally and internally. And there was an extremely high level of integrative efforts between applications and infrastructure teams, and compute and network were the primary infrastructure teams. The applications teams were, again, the business applications that had external facing web apps. Next slide. So I picked a really sophisticated analogy for network infrastructure and how it integrates to IP-enabled technologies. Next slide. So the applications, I want to check back into the applications ecosystem. So again, my focus is on primarily going to be on the application side and how it integrated with network infrastructure. So we have the systems management, and that means that the development, test, release, and update system management applications. The business applications themselves, this could be the legacy, on-prem, and of course web, mobile, and cloud. And they're all split by different teams. So multiple teams would have the same ecosystem for themselves. They're not necessarily centralized. Next slide. And then we have another layer is the application's life cycle. So there's always a matter of legacy, the ones that are live, and the applications that are transitioning. In the design process, we have to worry about development and test environments and teams, release systems and teams, and management systems and teams. Next slide. So I'm really focusing on the business applications, because the value of the IP address can be direct or abstracted. And we need to understand how those business teams are impacted by the value of an IP address. It also means that we have to really keep our evangelist hats on at all times, because applications teams are not necessarily so immersed in the V6 world as we all are. And they're constant. We need to really reduce the creation of new legacy applications. Every day that we don't address these applications, then there's just new applications released, and that just creates more legacy and more inertia. And we obviously don't want to have dual stack maintenance. It's just too expensive and complicated. And everything is just getting more and more complex as time moves on. Next slide. So incremental. So here's our sophisticated analogy. And so I've circled every point where the network infrastructure would integrate with another IP-enabled technology or application. It could be another, hard or soft. So every time there's a red circle there, then we have to figure out every time that water, in this case, network traffic flows, then we need to just make a determination if we're going to enable the next chain, the next section of pipe, or are we going to find a way to truncate it and not let the new traffic go. So every time there's a new intersection, there really needs to be a cross-functional determination of how you're going to handle that new traffic when it's flowing out of the infrastructure and into its applications. Next slide. The key challenges were I'm going to stick with the shared infrastructure and organization, evolution, and global configurations. And if we have time, I'll go into team best practices. But the three on the around the right, the top and left, sorry, are critical. So next slide. So the next couple of slides really shows how organizational evolution occurs, and we all know it does. But what does that do when they're all sitting on the same network infrastructure? So next slide. So as businesses grow and evolve, they're just adding more and more, and those teams end up under new leadership, new systems that they deploy. But next slide. But they all tend to still sit on the same network infrastructure. And so when we think back to that 69 authorizations that we needed to get, this is one of the primary reasons for that, is because the more teams share the same infrastructure, then you've got to make some deliberate decisions about, do you take everyone? Do you try to convince everyone to go? And if you've got global configurations anywhere in that infrastructure, then you've either got to figure out, are you going to bifurcate that by team, or are you going to really try to eat that elephant whole and try to convince all of those teams to go at once, because they're all going to be affected by whatever global configs you've got in shared infrastructure. So that's a very deliberate decision that has an enormous impact on your ability to move forward. At Cisco, I had the wind at my back. Cisco had a very strong inherent business reason for pursuing the way they did, but finance, retail, health insurance, marketing, manufacturing, they don't have that same driver. So the ability to get all these teams to go at once may not be as easy as it wasn't easy, but it may not have the same impetus that we had at Cisco. Next slide. Let's just skip this because in the interest of time. So again, just restating what I just told you. So the technology recommendations, one of the few of the things that made us successful is that I got all the teams together, and that would be external and internal. So I was able to gather our cloud providers and all the key architects on the applications and the infrastructure side. And we traced the IP address from its point of origination to the next hop. Where did it go? What happened to it? Where did it go from there? What happened to it? We walked that through all the way through the systems, and we were able to really reduce our risk by following that process. Again, global configurations are really going to be important. Again, do you bifurcate them and have your configurations, like your traffic profiles, be specific to a team, or do you just take all the teams at once and hope you can get them all to sign off? Method for flow transition, again, every single time there's a connection where the V6 traffic is going to bump up against another set of pipes that may or may not be enabled, you have to come up with a transition mechanism to make that happen. And then we didn't go over the teams, but another gotcha was security parity with V4 and those offshore offices. You can't always control what happens in offices you don't control, obviously. And so applications teams are constantly rolling on and off projects. They're much more dynamic in my experience than infrastructure teams are. So that makes it a lot busier in having to meet the requirements for those teams. Another thing I didn't put on the slide, but Happy Eyeballs is a fantastic tool. But the applications teams aren't so familiar with it. And so when it comes to your release window and you've got applications teams who are looking for consistent results before they sign off on something when they're doing their release window, and the expected behavior of Happy Eyeballs occurs, that can make them a little nervous. And so they may not get consistent results with V6. So I had the good fortune of having Andrew Yurchenko on my release window, but not everyone has that benefit. So he's still my personal hero. So that's something that you'll have to look out for with applications teams and getting them familiar when you're wearing your evangelist hat, getting them familiar with the expected behavior of happy eyeballs. Next slide. Yeah, so in terms of how the ops working group can help this process is developing a set of recommendations for handling that shared network infrastructure and the global configurations. We can't do everything, but having some high-level recommendations on where those points of integration are and how do you go about managing the global configuration so that you can be more incremental in your transition. The key applications, anyone who's talked to me for any more, in 30 seconds on this knows that I'm very strong about getting non-IT decision makers involved in this process because of budget. I think we're at a point where we need them to partner with us in order to move this forward. So it's really important to understand what those key applications are, meaning which ones can we tie to revenue, and how do you get those to move forward for your transition. And the recommendations for those points of integration, identifying the high level where those points might be, and then developing some recommendations for how those are handled. I think that's it. Okay, questions?
So I have a question from your leading of Cisco from IPv4 to IPv6 corporate network as the program manager. What do you feel is the most challenging thing? What do you have some kind of like lessons or insight that you want other enterprise to do? For example, do you feel that the difficulty is just get started? Once you get started, you will always reach that. Or before you start, you really should know this and know that, and maybe do this preparation and do that. Otherwise, you can start, but you may never get to the destination.
At this point, I think that it's important to get those other teams that may not be so involved in their V6 transition. I mean, we really need to move this forward. So in terms of enterprise, yeah, I think one of the key reasons we were successful at Cisco was they had already have a process called primes, and so they already had working relationships with the prime contacts in those key business areas. So that really helped in that when we built our communication strategies, when we had our communications announcements, it was really a lot easier knowing that we had the support of those key contacts in those areas. That would have been much more difficult to get, and they were key in getting the 69 sign-offs. It wasn't me getting all of them, it was partnering with those other teams and getting that done.
Any more questions? If no, thank you, Marie, and we go to the next presentation.
Thank you.
You are on.
Hello, can you hear me?
Yes, go ahead.
Okay, hi everyone. This is David Song from Alibaba Cloud. I work as a network architect. It's my honor today to have this chance to give a talk on IPv6 practice in Alibaba. Next slide. A very brief introduction on the company. Alibaba is famous for its e-commerce application like Taobao and Tmall. It also has applications for entertainment, travel, messaging, and working platform tools like Maps. It serves more than 1 billion users in China and 305 million international users out of China. In addition, Alibaba also served as a cloud infrastructure, including IDC, covering 28 regions with 85 available zones globally, and provide CDN services, DNS services, and cloud services. Large and small businesses develop their services and build its own application based on cloud platform. Next slide. First, I would like to briefly introduce the timeline and phases of IPv6 adoption in Alibaba. The first phase, I refer it as to research and preparing phases during the 2012 and 2017. People do evaluation, experiment, and a small IPv6 trial project inside this company. People think IPv6 is good, but not ready for commercial and production network. So during the period between 2018 and 2019, Alibaba started the IPv6 program to enable its core application and infrastructure to support IPv6. Carefully for each step, the IPv6 active users start growing. I call this phase as to small-scale IPv6 commercial adoption. And for the past 2 years after I joined this team, people have confidence and started to enable a larger scope of large scope of apps, regions, and cloud platforms based on the experience gained in early phases. The number of IPv6 users are soaring, and the IPv6 traffic ratio increased as well. You may notice the figures in the slides. I call this phase as the IPv6 fully deployment. And now we reach 1 billion IPv6 active users globally and achieve over 90% IPv6 traffic ratio in recent months. We test it every week. The next target in the coming years is to offer, not next slide. The next target of the coming years to offer IPv6 only capability for the users who only has IPv6 network. Okay, next slide. When we're talking about the motivation, I think that there are 3 things are common. And the price of IPv4 address are growing rapidly. The people doing IPv6, most of us notice that. And the government mandates, I noticed US has some mandates, and China also has some mandates to issue out the plans and policies to enhance the widespread adoption of IPv6 for protection network and services. And it also creates some market space for the customer who also need to follow the plans and mandates, and the customer requires the IPv6 capabilities during the process. And the third one is IPv6 innovations and new capabilities. There are a team of inside of our company focus on the software-defined network based on SRv6 towards a fine-grained network services for application. As to the challenges for online services, the scalability and risk issues is a matter of primary importance for large-scale online services. And the legacy infrastructure must support new services. We cannot stop and wait for IPv6 adoption. It introduces complexities, risk, and additional works for us. When Alibaba started its IPv6 commercial adoption in 2008, early 2008, the end-to-end network is not ready for IPv6 commercial use compared to IPv4. So it also adds some challenges. In addition, it's not easy to coordinate 20 different business units and more than 500 engineers work for one project. So in the following slides, I will focus on some technical considerations for engineers. The first and the primary technical challenge is how to migrate online services smoothly without interference of users and operating applications. The second one, a sub challenge is how to measure the quality of IPv6 network and adopting dual stack environment. And I will also talk about the small technical considerations regarding to IPv6 MTU. Next slide, please. To better understand how to enable IPv6 for online services, in this page there is a very high-level online services architecture. You can see there are three parts. One is the user-side application or browser, DNS, and ISP network. They are supposed to support IPv6 in the first place. Extensive effort has been taken in the Alibaba team to enable apps to adapt to that dual stack. I will talk about it later. The second part is the access point of application, which receive IPv6 connections from users, go through security checks, and deliver it to the best application service which handle the connections. It should be upgraded to provide public facing services. And we also have third part is the cloud services for cloud VPC users. They are inner-facing services. Some people hope that IPv6 only adoption in inner-facing services will relieve the stress of IPv4 private address use. But it's not the highly priority right now. Okay, next slide. From the cloud platform point of view, there are three solutions for different user requirements. The first one is the proxy solutions. In Alibaba Cloud, we adopt some solutions like the global accelerators, which enable the IPv6 capabilities for public-facing access. No change are required for the legacy infrastructure. For users who already deploy their services on the cloud, they can choose the load balance 6-4 or dual stack 6-6 load balance, just as Alibaba apps do. Now, Alibaba Cloud has full capabilities of dual stack. Generally, the idea is we want to decouple the IPv6 adoption on public-facing IPv6 services and the legacy application. The ultimate goal in our plan is to enable IPv6 for all APIs and system calls for each transactions, including the cloud services. Next slide. Okay, let's focus on the major technical challenge I proposed in previous slides, how to migrate online services smoothly. Firstly, we should understand the quality of IPv6 network. Nowadays we have. In Alibaba, we have application performance measurement platform looking into the status of IPv6 network performance. In this page, there are some metrics like TCP success rate, RTT, IPv6 coverage, and some broken Wi-Fi issues. From the TCP success rate and RTT, we can find that in the early phase of like the early 2018, the end-to-end network is not ready for commercial use. We have only 75 success rate and almost 215 microseconds in the early 2018. So by the efforts of joint efforts with Chinese ISPs like China Telecom and Mobile, Alibaba optimized the end-to-end IPv6 performance and reached the requirements of commercial services today. The coverage of IPv6 is also a very important metrics. In the early months of this year, it's around 90% and almost widely deployed in the mobile LTE network. The coverage is very low in Wi-Fi access network. We also noticed that in the dual stack Wi-Fi network, many users may experience failures due to the broken Wi-Fi routers or routing settings. There are many failure cases we connected. Next slide. Okay. Okay. Generally, we do 3 measures on the apps when we find that it's okay to open the IPv6 for each users, for each group of users. Firstly, we do measurement to pre-detect the quality of IPv6 network as I introduced previously. And the second one is the push configurations and content to specific user groups based on different factors like geolocation, the Android or iOS platform, or ISP networks. The third, an improved Happy Eyeballs implementation adopted using, we combine the DNS response with port A and A. We also push the priority address list by the server, and we maintain the state of each IP port protocol tuples other than just the IP. Next slide. To increase IPv6 ratio for the apps, for example, the Taobao app, for example, we make a list of domains to be IPv6 enabled. There are more than 500 domains in Taobao, for example. Priority is set to first to enable the CDN domains and domains related to resource on the first page, for example. The apps also pre-pool IPv6 address of domains if they can use IPv6. It's worthwhile to mention the behavior of apps in the dual stack environment when the IPv6 is allowed to use. In the early phase of IPv6 adoption, 30 minutes penalty was set for each IPv6 failures because at that time, in the early phase, the quality of IPv6 network is poor. In order to increase the traffic ratio of IPv6, the app tried IPv6 first and fall back to IPv4 if finished. It works good for mobile network, but fall back recently in broken Wi-Fi situations. Now we reach IPv4 and IPv6 in a connection time delay 300 microseconds, and as a Happy Eyeballs suggested. So with these approaches, many Alibaba's applications, including Taobao, reach more than 90% of IPv6 traffic ratio in mobile LTE network. Next slide, please. Okay, there's one issue that we are tackling recently regarding to the IPv6 MTU. We all know that IPv6 packet is prone to be dropped due to the middlebox like firewalls and the nets, etc. To avoid failures caused by IPv6 packet drop, years ago, my colleagues chose a very prudent value for the IPv6 MTU and TCP MSS, as we show in the slides, which decreases the transmission efficiency compared with IPv4. Now we are going to test and implement larger IPv6 MTU and TCP MSS in CDN environment. Next slide. Okay. 5 years ago, in 2017, I was invited by the Epinic to write a post on IPv6 in China. In that post, I summarized the state quos and identify speed bumps of IPv6 at that time. 5 years later, where are we now? I just compare what I post in that post, and we found that we have good news and good aspect that fully connected IPv6 production network has been built, because at that time, 5 years ago, the IPv6 network is fragmented and some trials and islands. And IPv6 penetration is over 90% from the view of Alibaba's apps where LTE network, but it's poor in the Wi-Fi network. The IPv6 traffic increase from the authority data are more than 14% in LTE network and 10% in the main network. The IPv6 performance is almost close to IPv6 V4 and better than IPv4 in some cases. We did some tests inside Alibaba, and we found that dual stack is proved to be the best approach of adopting IPv6. Yes. There are also some better aspects. The last mile issue still exists. We still have long tail user side network to be upgraded. And IPv4 address price still hurts more and more. And dual stack may last for a long time due to legacy network and systems. So it's very hard in short time to relieve the IPv4 address price burden. Currently, I didn't notice any plans or paths in the community to sunset IPv4. Maybe I missed something important. Next slide. Next slide. Yeah, okay. As a conclusion, I think IPv6 is fully mature, and Alibaba's upgraded infrastructure and application in less than 5 years, and now enable 1 billion IPv6 users globally. We notice that stability and risk control are crucial considerations for large-scale online services. Alibaba put a lot of effort to ensure the smooth transition and found a path to deploy IPv6 in large scale. Keep IPv6 in considerations in the first place because upgrading legacy infrastructure is very hard and hurts a lot. It's much more complicated than a new one. So in Alibaba Cloud, new products and new version of products are now required to support IPv6 capability as a veto. So the last conclusion is that the dual stack is the only approach. We proved that. However, I think from personal view, the IPv6 community should consider a countdown timer for IPv4 because they're obvious that IPv4 and V6 are competing in some cases. The users have the hesitations to adopt IPv6 if IPv4 is still available. So that's my observations. That's all for my presentation. Thank you.
Thank you. Fred, you are on.
Yeah. Any questions?
Yeah. You mentioned that there is no sunset plan for IPv4 and that the IPv6 community should consider a countdown timer for IPv4. Now, Lee Howard has spoken a couple of times targeting a sunset plan for IPv4, and people have kind of said we're not ready for that yet. Are you saying that Alibaba is?
I'm not saying that Alibaba will count down the time. From my observations and some experience from the dual stack adoption, it's very key for the client side. I mean, the users, most of users migrate to the IPv6 or dual stack. Then the service provider or content provider should most likely to follow the step. That's the successful path for the dual stack deployment. I personally think that it's also a good path. Firstly, to sunset IPv4 in the user side access network, for example, the LTE network, and then maybe the time for the ICPs. Yeah.
I don't see the users in any hurry to sunset IPv4.
Yeah. Yes. That's the question. I just proposed with this chance. If we maintain the dual stack, their dual stack is always there.
Okay, Robin.
Hello, Lin
can you hear me?
Robin.
Sorry. Hello? Hello, Linjian, can you hear me?
Well, Cheng Li, then please go ahead. Well, if not, Mike, you can go ahead.
Hi, Mike Ackerman. First off, thanks for doing a great presentation, and we need more like this. Early on in your presentation, you mentioned that the motivations for going to IPv6 included V4 pricing. Can you elaborate on what that means a little bit?
Enterprise, the big companies, big companies and the platforms like cloud platforms companies, they need IPv4 address to scale the network, to provide services for their customers. They continue to buy IPv6 from the market. The price soar. Maybe you noticed that or not, that there are full $15 for each IPv4 address. As far as I know, it's reached that high. Yeah.
Did you have to buy more blocks of IPv4 addresses to support legacy users or any special situations? So I'm really asking if there's hard dollar costs there for you.
The address provide for new services, and your network will increase the size, right? You need to open more public services for your clouds customer. There are many situations that you need public IPv6 address, I think.
Okay, that makes sense. And one of your other driver factors was V6 capabilities. Other than the number of addresses, can you elaborate on what the additional capabilities that attracted you to V6 were?
Yeah, actually, I'm not a very has expertise on the extensions of V6. But another group of our team, they are focused on how to leverage the extension options of IPv6, the segment routing to build a software-defined approach to better choose the path. That's how we're looking forward that the more traffic can migrate to IPv6. Then we can do the scheduling for each applications. Yeah, that's why the current target right now is to increase traffic. If there is no traffic in the network, there's no requirement, no urgent requirement to use that capability.
Okay, that's fine. Then that makes sense. Thank you for that info again.
Robin, are you still want to speak? Cheng Li? If not, Chong Feng will go to you.
Hello.
Edward?
Can you hear me?
Yes.
Okay, I have one question about IPv6 only for cloud data centers. You have mentioned that IPv6 only will be the ultimate stage of cloud platform and cloud service, right? You know that cloud data center hosts the VM or VPCs for customers, right? So my question is, your definition of IPv6 only is based on the assumption that the VPC will be IPv6 only or dual stack. If the VPC can be dual stack, how to support dual stack VPC in IPv6 only cloud with South Coast? Okay.
Okay. The uh, the VP6 runs on the overlay, right? It's not required. It's not a must to require the V4 capability to support that overlay. So in IDC, it's just to provide a tunnel similar like tunnel like the VXNAM technologies. So the VPC can run dual stack and the IDC can run IP6 only. But right now it's not achieved that phases. Right now the all traffic can run on the IPv4 as a tunnel. So that's the field that we need to fill. Yeah.
Okay, thank you.
Hello. I have a little bit similar question to the previous one, but if in the future you will have IPv6 only application, then probably you will still have somewhere small number of users which are IPv4 users. And in this case, you will need some network address translation. On your slides, I have seen network address translation from 6 to 4, but I have not seen a plan in opposite direction from 4 to 6, because in the future, definitely you will have a small number of users which would be IPv4 only, and you will have IPv6 only applications. Do you have a plan for load balancer or network address translation or something to translate from 4 to 6?
Well, it seems like time is up. So our session.
Actually, just one quick note. Even though Fred isn't leaving us now, I wanted to quickly take a second to thank him for 17 years of service and having served as a really great V6OPS chair. As Fred said, this isn't goodbye yet, but he did indicate that he's potentially interested in leaving. Whether or not we'll let him actually leave is a separate question. But I'd like to say thanks to Fred. Drop him an email thanking him. And yep, that's it. I'll give it back to
Our session ends here, so please take the issue to the next. Thank you very much for attending the V6OPS sessions. I think that it's probably big factor. Pardon? It's big factor. So
Yeah, I think you're in the view of the thingy. Yeah. Whatever. Now we know.
Yeah.
All good. Cool. So I think that went okay.
Yeah. So I think that we try this operation presentation. I think the last one was maybe the 6 over here. Yesterday.